what if I told you that you, me, and everything that exists, everything that you can see around you, everything that exists in the universe is just some sort of melody, like music that is played out of some field. And that field is known as the quantum field. You know, uh, matter is the building block of everything that exists. And matter is made up of atoms. So the building blocks of every matter are atoms, and atoms themselves are subdivided into, particles. You have electrons, protons, and so on. So you really have, at the most fundamental level, these tiny entities, these particles that make up matter, which in turn makes up everything that you can see around you. So I'm going to take you to my whiteboard, and in order to explain what this field is all about and how it actually manifests itself, let's maybe start with some classical analogy. So a good starting point here is what's known as the classical harmonic oscillator. So a classical harmonic oscillator, just picture out maybe a mass that's tied to the end of a spring. So something like this. And you probably recall from secondary school physics that the potential energy of this spring, of the mass, can be defined in terms of Hooke's law. Like, you suppose that the force obeys Hooke's law, thus the potential can be written as half kx squared. So it's parabolic, which means that if I sketch it, so here I can see the energy. You know that the potential is just like the energy contained in this system, not the total energy, but the energy kind of due to the spring. And this is just a parabola like this, which means that this particle, at this point, it has its minimum energy, and then it can move, it can swing up and down following this path. So this is like the classical harmonic oscillator. Now, it appears that if you want to describe microscopic processes, then you need something a bit more sophisticated. This won't enable you to understand microscopic processes and their interactions. Then comes the quantum harmonic oscillator, which of course is based on the principles of quantum mechanics. So the idea is kind of the same thing. Your potential, you would still describe it, as Hooke's law potential if you want. So this K, I think, is like M, H, and something. This K is like a function that would depend on the mass, then the Planck's constant, and so on. But the potential can be written thus. But then, if you want to sketch it, you're going to have something like this. But the main difference with the classical harmonic oscillator is that all energies are not allowed, which means here you're going to have you have the ground state, okay? And the ground state has a certain energy that you get by solving the Schrödinger wave equation. So that energy, actually, they correspond to the eigenvalues of the wave function, and it's given by n plus half times h psi omega. So we can call this En, which means that in the ground state, so when x is 0, if you want, is going to have, so actually when n is 0, the energy is not 0, as you can see here. E0 would be like h side omega over 2, which means that n equals to 0 will be some point here. That would be E0, okay? And then, in order to move to the next energy level, you need some quantity. You need to absorb like a definite amount of energy. So in this case, That's going to be h psi omega. So you're going to have these discrete energy levels and so on and so forth, which means that a particle that has a potential, okay, described by this quantum harmonic oscillator, would only have certain allowed energy levels like E0, E1, E2, and those energy levels, you can see they are quantized by this amount n. So that's the main difference. And then, if you want, as a bonus, the wave function, which encodes the probability density or the probability of finding the particle somewhere in space, then would be defined by a set of polynomials. In this case, they are Hermite polynomials, but I won't go much in depth. But just to give you an idea, in the ground state, it's going to be like a Gaussian. And as you go up, you're going to have several functions, like several polynomials, and so on and so forth. So now, how does this relate to our quantum field? Because that's the main idea. Because that's what we want to understand here. So you will have to picture out like the universe, or the quantum field as maybe a box. But actually, this box is infinite. And inside this box, you have springs. So let me draw them. We're going to have springs, okay, that are coupled in 3D. Yeah, so you have like springs that are really like connected to each other in a three-dimensional space. And these springs have like distinct frequencies, or they oscillate at different or various frequencies. So particles then appear to be excitations of this field, which means if you create like a perturbation, let's say at this point, it's going to propagate all through the field. And that propagation, okay, in the quantum field, you can picture it as a bump that just propagates, all through the space around it. So these are particles. So this field could be, I don't know, the photon field, or it could be the electromagnetic field, or maybe the Higgs field, as you wish. But then the particles that emanate from these are just excitations of this field. And then if you want to consider the fact that these springs are actually connected to each other, it means that interactions can occur between various like modes, okay? And these interactions, if you want in practice, would account for processes like nuclear decay or any other interaction, okay, that involves like two particles. So you get it, kind of the big picture. These particles make up matter, and then matter is just everything that you can see around you. You are matter, I am matter, and anything around Earth is matter. So this is kind of what quantum field theory has to tell us about the universe, like the description it can give us to the universe. Of course, there are subtleties that have to be taken into account in this general idea, the theory. Here, I just gave like a big picture to get you a sense of it. But you get it, we might just in the end be melodies, okay, that is played out of, fields that exist out there. Do you find this interesting? Do you think that this theory, which is one of the best that we have succeeded to develop to date, would enable us to explain every phenomena that we might encounter out there in the universe already? Of course, there are some shortcomings, but this is something that gives us a very good understanding of what is out there. Your opinions about this in the comments.